Hello, my name is Phoenix-Avery Sarían, and I worked with Doctors William Colton and Fiona McCarthy on separating the cosmic ray background from the kinetic Anisotropies effect using wavelet phase harmonics. The CMB is radiation from when the universe is 300,000 years old. A snapshot of the early universe is crucial for understanding dark matter and cosmic structure, but is contaminated by secondary signals introduced as the universe evolved. To study the CMB precisely, cosmologists will combine data from telescopes like Planck and the Atomic Cosmology Telescope to better isolate these signals and extract detailed cosmological information. One particularly tricky contaminant is the kinetic Sun-Yuzadovich effect, or the KSC. It occurs when CMB photons scatter off electrons to galaxy clusters, moving relative to CMB rest frame, causing subtle temperature shifts. Because the KSC overlaps with the CMB in frequency, you can't separate them using standard multi-frequency methods. The key difference is that CMB is mostly Gaussian, while the KSC is non-Gaussian with coherent structures tied to cluster motion. The KSC temperature shift is proportional to the cluster's optical depth and line of sight velocity, with the sign indicating whether the cluster moves toward or away from us. This brings us to our essential questions. How do we separate these entangled signals while traditional techniques fail? We decided to exploit their structural differences. Specifically, can wavelet phase harmonics recover the KSC by targeting the CMB's Gaussian nature versus the KSC's non-Gaussian features? When we look at the power spectra, we can see how temperature variance distributes across different angular scales. At large scales, the CMB dominates with prominent early universe fluctuations, but at smaller scales, there's a crossover point where the KSC from galaxy clusters becomes stronger. This is exactly what statistical separation techniques like ours become essential. In our simulations, the CMB shows smooth, large-scale Gaussian features, while the KSC appears as granular, small-scale fluctuations from electron motion across cosmic structures. Their structure is fundamentally different, which is a key to our separation approach. But the challenge is that we only observe their sum. A tangled mix where the CMB dominates the KSC is much fainter. When we look at the combined signal, there's no obvious way to visually distinguish between the two components. We tested simple power spectrum filtering to suppress KSC structures and recover cleaner CMB. While this basic approach demonstrates the difference between Gaussian and non-Gaussian components, is inefficient. It ends up discarding signal we actually want to recover. We're working with an observed map with the sum of the KSC signal we want to recover and the CMB acting as a contaminant. Since both overlap in frequency and scale, we had to rely entirely on statistical differences. Our approach uses two categories of wavelet phase statistics. The S00 coefficients measure wavelet power at various scales. The CMB has a well understood power distribution, while the KSC is flatter and more irregular, so S00 highlights where they diverge. The C phase statistics assess phase correlations across scales and are particularly sensitive to the coherent non-Gaussian KSC structures from bulk flows and clusters. The Gaussian CMB shows much weaker phase coupling. By combining these, S00 for energy distribution and C phase for structural organization, we can detect the subtle KSC signal embedded in the CMB and improve the precision of cosmological measurements. This work is especially relevant as the Science Observatory Large Aperture Telescope enters operations. With its high resolution and sensitivity to small scale CMB fluctuations, it is well positioned to detect the KSC. Our wavelet phase harmonics approach provides a complementary tool for extracting the signal from upcoming data, helping maximize the scientific return from this next generation experiment.